So contents of my presentation today we'll first be talking about why computer-aided drug design is important. Then we'll be talking about what is diffusion as a machine learning architecture and how can it be applied to drug design. And then finally, the results and special features and limitations of this DiffSBDD, the paper. So why do we need computers to help drug design? For every drug that hits the market, around 5,000 to 10,000 compounds are considered over a process that takes 10 to 15 years and almost $1 billion. It's extremely costly, it takes a lot of time, and many of the 5,000 to 10,000 compounds are irrelevant and wouldn't be good candidates for a drug. So computer-aided drug design can help filter out good candidates or select high-quality ligands so pharmacologists don't have to test as many in the laboratory. So what is computer-aided drug design? Computer-aided drug design is trying to generate certain drugs, aka the ligand, and based off whether the protein 3D structure is known or unknown. If it's unknown, we have to focus on the ligand and which parts are good for drugs or which parts should we try to change and adjust. If we know the protein 3D structure, we perform structural-based drug design, where we identify the binding pocket and try to simulate molecular docking, where we orientate the ligand to bind to the protein and see binding affinities and others. So our goal is to generate a batch of high-quality ligands to bind to the specific protein pocket. What do non-diffusion generation methods use for this task? So autoregressive and RNN models, they essentially work on smile strings. Smile strings is like a sequence of letters that represents a molecule. They add one atom at a time. So they take this smile string, and let's say you should try to generate another atom. They would add one more atom at the end of this and consider the probability of what is the next likely character of this atom. So is it likely to be oxygen, a nitrogen, or even a like sort of double bond or single bond? This doesn't really model how molecules are made in real life, because in real life, molecules aren't just added one atom at a time, but you have to consider the complete whole.
Are atoms only added to one end or the other, or can they be added in various places throughout the molecule?
I believe in autoregressive and RNN models, you start off at like one atom, and then you add 1, 2, 3, 4, 5, and so on. You just keep on adding to that.
So adding to the end?
Yes, I believe so. So I'm going to propose a little analogy for diffusion to help you explain. So imagine you have to generate 1,000 stick figures with triangle heads. This triangle head kind of represents the characteristics of how the ligand should bind to the protein. Now, if you were to generate by hand and try to code an algorithm that says, I'm going to draw the triangle and then I'm going to draw the characteristics of the stick figure, you're going to probably run out of variations to draw. So instead, we're going to try to generate it through diffusion, which is adding noise and subtracting noise. So diffusion has two processes to train. First is the forward process and then the backwards process. So imagine we take a ligand, this our benzene molecule. This wouldn't be a realistic ligand, but for the sake of an example. We take apart the covalent bonds and then we continuously add noise over 1,000 steps. So we move the positions of the atoms, maybe we swap one of the atoms out for another atom. And then finally, we get something that's like pure noise. It doesn't make sense as a molecule. This happens the same thing for DiffSBDD, where we start off with the molecule, and eventually we get something that's pure randomness.
Eric, question. With the adding the noise, are you following any set of rules or just random picks and deletions of atoms and additions of different atoms?
I'll get to this in a minute, but you kind of encode the molecule as like this Latent vector. I'll explain it in a minute. Okay. So after you forward noise a molecule, so it's like pure randomness, you have to trace it backwards step by step, and you use a neural network to do this. The reason why this is possible is because you kind of add in noise like one step at a time, only based off of the previous step. So it's traceable. So imagine like after 1,000 steps, you trace it back and you get to this molecule. So now you have a model a reverse denoiser, you can call it, that takes in a sample of noise and then can trace it back to the original molecule. In our stick figure analogy, you can take this part of noise and then trace it back to what the original image was. So what do you think happens if we put a new sample of random noise? If we arrange the random noise in a new way and pass it into the denoiser, instead of getting an existing ligand that we trained off of, we'll get something totally new and different. And now this has simplified the problem greatly. Instead of generating 1,000 molecules, we simplified it to generating 1,000 random samples of noise and then passing it into the denoising model. So to put this all together on how this works into DiffSBDD, first, we can't actually do this noising, denoising process on atoms and bonds. The computer doesn't really understand that. We have to first convert it to a ligand vector, which is converting this molecule into a 1D list of numbers. Secondly, the reason why this whole noising process is possible is that we only add in reverse noise step by step. So you consider step 0 and then you add noise to get to step 1, and only step 1, the state of step 1 is considered when you add noise to get to step 2. By doing this, we are able to trace back from pure noise all the way back to the original ligand. DiffSBDD also follows this framework similar to what I was showing you, where it adds noise both to 3D positions and maybe changes up the atoms, and then it reverses noise until it fits back into, for example, a protein pocket. So the whole diffusion process considers like how it will fit into the protein pocket while it does it. And then at the end, it adds covalent bonds where it thinks it makes sense. In order to generate new molecules, we also have to figure out how do we represent these molecules to computers? Well, the obvious answer would be as a graph. So just like our benzene atom here, we have nodes that represent atoms and edges that represent bonds. Now, these edges don't necessarily represent chemical bonds in a sense, but they just represent pairwise interactions between atoms. So these hydrogen atoms here, although they're not directly bonded together, can be considered as an edge in the graph, and like certain information such as the distance and also like the type of bond or will be considered. Not only is ligand to ligand interactions between atoms considered, but also the ligand, our inhibitor, to the protein, which is really important for understanding how the ligand affects the binding pocket. For the nodes, we consider chemical characteristics such as partial charges, the element type obviously, hybridization, but also the 3D coordinates of where they are in space. DiffSBDD, one of the reasons why it's better than other diffusion models currently, is that it kind of enforces SE3 equivariance. So it respects the natural symmetry of what happens with molecules. So remember how I talked about how these atoms are represented in 3D space? We don't want the model to consider it a new molecule if we translate it, if we shift it a certain like 5 units, or if we decide to rotate the molecule, it's still the same molecule. However, reflection is considered distinct, and the reason why is this chemical property known as enantiomers. So enantiomers are molecules that are mirror images of each other, but cannot be superimposed on each other. So for example, let's say your left and right hand. They're obviously mirrors, right? But you can't put them on top of each other. Same thing happens for molecules. For example, the famous drug ibuprofen, more commonly known as Advil, in its S+ enantiomer stage, it's active and it has biological properties, while its R-, as you can see, is flipped, it's mirrored over, it's inactive. How do we know that DiffSBDD is better than other models? So first, there are 4 different models considered as part of the author's table. We have DiffSBDD conditional, which where the whole ligand is generated from scratch, so it's a complete de novo design. DiffSBDD joint, where part of the ligand is fixed, so certain atoms, certain sections of the molecule remain the same, and pocket to mole and ResGen, which are two other competitive models. The data sets we used were crosstalked and binding MOAD. These two data sets contain proteins and ligands, so you can try to run these models on the certain proteins to generate ligands. So you run DiffSBDD on all the crosstalk proteins, you pop out some ligands, and you compare those ligands to the real existing ligands used in the test data set. The numbers here represent Wasserstein distance, which represents how different the two data distributions are. The lower the number, the better, and the bolder number is the best in its certain data set and category. The Wasserstein distance isn't just evaluated for like how different the ligands are in distribution. They're evaluated for how different the ligands are for a certain metric. So, put a short example, let's say this number, 0.0187. We run DiffSBDD join on the crosstalk proteins to generate a bunch of ligands. Then we measure the QED, aka the drug likeliness of those ligands, compared to the QED, the drug likeliness on the crosstalk ligands. And we run the Wasserstein distance to see how different is their drug likeliness. So how realistic is DiffSBDD? And it turns out it's pretty realistic. So other metrics used are SAS, which is synthetic accessibility score, log P, which measures hydrophobicity, Lipinski, like how well it's orally available, Venus score, which is like some binding energy, and then CNN, which uses a convolutional neural network to predict binding energy. As you can see, not only does DiffSBDD have the best metrics in many categories, it's bolder the most times, it also has the lowest runtime. Current limitations and future directions. So first, DiffSBDD models the protein as a static fit. Imagine this is the binding pocket. When ligands bind to proteins, the binding pocket changes shape to adjust to ligand. However, DiffSBDD considers the protein in a static shape. It doesn't change the protein based off of the ligand, which doesn't model reality. So a future step could be to consider the ligand docking as part of the cost function and how the protein conformation will change. Another limitation is that it doesn't have reinforcement learning on metrics. It doesn't consider in its generation process how to optimize for a certain metric such as SAS or QED. Instead, it just tries to generate towards the binding pocket. So, key takeaways. Diffusion is an innovative way to generate molecules, and it's not one at a time. So it models how biological molecules are more realistically compared to autoregressive models. It's the first SE3 equivariant 3D conditional diffusion model for structural-based drug design. So it respects the rotations and translations of molecules in 3D space. And just a fun fact, diffusion used for molecule generation was inspired by diffusion for image generation. So when you use DALL-E or ChatGPT for image generation, this is the same architecture. So any questions?
So this is like a pretty idealistic approach to like the generation of molecules. You know how feasible it is to actually like synthesize these artificially like generated molecules and drugs?
Depends if you optimize for like a certain characteristic. So like here you can see like there's a synthetic accessibility score, and what DiffSBDD does, let's say you want to optimize this synthesizability. It generates molecules and kind of does like a natural selection. So the worst like SAS scores are eliminated, and then it reruns generation with these new training set of ligands. So it kind of modifies the best SAS scores to try to create even better SAS scores.
Do you know what pocket to mole does differently that makes it like significantly more synthetically accessible?
I believe pocket to mole considers like, I remember ResGen considers like how the residues of the protein interact with the ligand. Pocket to mole, I think, considers more of the binding pocket rather than the ligand in terms of generation.
doesn't learn based on the metrics that it was like scored on. How is it like so much better than like the other ones? Is it just because it's using diffusion and the other ones aren't?
I think one reason is like that SC3 equivariance I talked about before. So other models don't enforce this SC3 equivariance, so they consider like rotations of the same molecule the same, so that gives DiffSBDD one advantage. Another advantage, I guess, would be how like DiffSBDD, although like other models also consider the binding pocket, DiffSBDD generates directly within the binding pocket throughout its diffusion process. So going back to a previous slide, this like blue part around here represents like the protein's binding pocket. So as you can see, like the ligand is being generated with consideration to the protein pocket, like at every step of the way.
The two data sets, I don't remember what they're called. Do you remember, or do you know the difference between them? The binding mod and the cross-off? I don't know if you mentioned that.
I believe that, I think one of them has more like existing ligands and proteins. The other one was like specially curated, I think maybe with like computer generated ligands, but I'm not too sure. I'll have to get back to you on that one. Julia?
You have a slide that was when it's like noise and then noise are like what it makes, like how does the denoiser know which molecule it's creating? How do I specifically recognize that it knows?
Like how does the denoiser work?
Yeah, like how does the denoiser make the molecule from that noise? Like
Yeah, so I think, like, first of all, it considers like the final state of the ligand. So you can kind of train a neural network to, let's say we start off with this sample of pure noise, and then the goal was to get back to this ligand. Afterwards, you can evaluate, oh, how similar did you get to this ligand? If it's not similar, you update like kind of a cost function to adjust how it denoises. And the denoising process of why is it possible to go from this random bit of noise back to like a coherent, making sense molecule? The reasoning behind that is because diffusion in general acts as like a Markov chain. So diffusion is applied step by step, where you add noise one step at a time for 1,000 steps in a row, and each step is only affected by the previous state. So you can kind of like backtrack like 1,000 steps to denoise the noise after the ligand. Derek?
Do you have any examples of like any like molecules that were like generated through DiffSBDD? Because, yeah.
I believe this was one. This was a generated molecule. I mean, there were some in the paper, but I didn't include them in the slides.
Has any of them like been like used for like any purposes right now, or like are they still like are any of them like synthesized or no?
I don't believe so.
So that would be the next steps then, right? Would be to try, if they find a really good candidate, to try to see if it's,
Makes sense.
to actually like
Yeah.
test their model. And I guess that was gonna be my question, was sort of like, has this been used at all in a way that they can see some benefit clinically or even in the lab at early stages?
I don't.
Or is it
not-
too new?
not that
Are we
much.
too
I think
new?
it might be too new. Yeah.
Okay. I will say that molecule looks like potentially a reasonable molecule.
Yeah.
Like some of these other circle ones I've seen from you guys in the past. So I like that.
Any more questions? All right, thank you all for coming. If you guys want, take a video on the way out.